Hello guys, welcome back. This video is gonna be about the ggplot2 graphic system. In our last video, we introduced the base plotting system. The base plotting system contains many useful functions that allow us to create a variety of statistical plots. For now, you've already gained some hands-on experience with the base plotting system through our lecture and exercise examples. And we could feasibly do anything we want in base graphics. However, instead of representing data in terms of x and y coordinates, the base plotting system has no built-in support for encoding additional information, especially categorical information, where graphical elements different aesthetic properties like color, marker shape, light type, etc. For instance, to plot multiple data series for weekly stock prices, we need to do manual subsetting and plotting multiple times to add multiple curves separately and color them differently. Even after we've arranged the data into the tidy format and hand a company variable that defines how weekly prices should be categorized. So when doing plotting in base graphics, users bear sole responsibility for explicitly constructing and rendering graphical elements, and specifying their symbols, colors, sizes, etc. to encode the grouping information for better describing the data. Besides, ending the legend is also manual. So you may wonder, is it possible that we just tell the plotting system what colors of line segments we want to use for different stocks, and the system can then group weekly prices accordingly and plot them with line segments of different colors automatically on our behalf? Another awkward workflow happens when we want to group multiple related plots together and juxtapose them to give some sort of comparisons. Users must deal with setting up the plotting grid, laying out the individual plots, working to keep axes consistent, reducing redundant margins, and many more. And this overhead can swiftly become extremely annoying. In sum, although base graphics is suited to do quick plotting for data exploration, creating complex graphs in base graphics is time-consuming, and it is nearly impossible to create complicated overlays in base graphics. This gives rise to the need for introducing the second plotting system, called ggplot2, for data visualization in R. So what is ggplot2? Basically, it is a package in R that we can download from the comprehensive R archive network, and it's a data visualization piece of the tidyverse collection. ggplot2 implements what's called the grammar of graphics, a theory that describes how all kinds of data or statistical graphics can be broken down into a set of abstract concepts. So what is the grammar of graphics? Let's think of the grammar of a language like English. You have things like verbs, nouns, and adjectives. And you can put them together to form sentences. Analogously, the grammar of graphics kind of describes those basic elements so that we can put them together to make new types of graphics. Just like you can take a verb and a noun and an adjective and make a new sentence that maybe no one has ever heard before, you could take the grammar of graphics and put together various aspects of plots and make a graphic that no one has ever seen before. Now you may wonder, what are the verbs, nouns, and adjectives of a data or statistical graphic? In brief, the grammar of graphics tells us a statistical graph is a mapping from data to aesthetic attributes like color, shape, size, etc. of geometrical objects like points, lines, bars, etc. The plot may also contain statistical transformations of the data and is drawn on a specific coordinate system. Van theta may also be used to generate the same plot for different subsets of the dataset. And it is the combination of these independent components that make up a graphic. So, with the grammar of graphics, we can succinctly describe a graphic in terms of data, geometric objects, aesthetic properties, statistical transformations, and so on, and create the graphic we have described. It allows us to produce graphics use the same structured thinking that we use to design an analysis, reducing the distance between a plot in our head and one on the page. The grammar of graphics was first implemented in R as a package called ggplot, and ggplot2 is its current implementation and was officially released in 2007. Since then, ggplot2 has grown in use to become one of the most popular R packages. ggplot2 further adapts the grammar of graphics to have a layered structure, so as to render different graphical components in a structured way. Generally speaking, ggplot2 has a slightly steeper learning curve than the base graphics system. Although the conceptual framework in ggplot2 can take a bit getting used to, once mastered, it provides a very powerful language for concisely expressing a wide variety of plots. And it generally produces far better and more easily customizable graphics. Okay, let's start to learn the basics and some useful recipes to make plots with ggplot2. The starting point for creating a plot is a set of data to visualize. The ggplot2 library comes with a dataset called MPG, short for miles per gallon, which contains fuel economy data for 38 popular models of cars. In fact, this dataset suggests many interesting questions. For example, how are engine size and fuel economy related? Do certain manufacturers care more about the fuel economy than others? We'll try to answer some of these questions by creating plots with ggplot2. And this slide gives you a glimpse on the types of variables contained in this dataset. A ggplot2 plot starts with a call to the ggplot function. This function is mainly used to declare the input data frame for a graphic. In this example, the MPG dataset. We also use a function called AES, short for aesthetics, to specify a set of aesthetic mappings that will be used throughout all subsequent plotting layers. Here, the two named arguments indicate which variables should be mapped onto the x and y positions of the geometric object to be plotted. In this example, the x-axis is the displacement, or actually the size of the engine of a car, and the y-axis is the mileage on the highway for that car. The output of this AES function is passed to a parameter called mapping to establish static mappings. Once a mapping is established, the values of the variable are used to generate values of the static. This call creates a new ggplot object. I assign it to the name p so as to be later used and added to. As you can see, the output is an empty panel with axes and labels. And this panel has a slightly different appearance than those created by the base graphics system. It has a gray background with white grid lines. But other than this bounding box, there's nothing to see until we define what geometric shapes we want to use to display the data and add a layer of them. In ggplot2, a plot is built up in layers of geometric shapes. Suppose we want to denote the data by a set of points. We simply use the function geom_point to create a layer of points and overlay it on top of this panel by using this plus sign. This is an important usage pattern, and as we learn more about ggplot2, we'll construct increasingly sophisticated plots by adding on more and more layers. As a result, we have this scatter plot. Now you can see how the mappings we just specified take effects. The displacement and the mileage on the highway are mapped to the x and y coordinates, or collectively determine the positions of these points. A scatter point alone could be hard for us to see some dominant pattern. In this case, it could be useful to add a smoothed line to the plot. So we use the geom_smooth function to add a layer that contains a smoothed line estimated from the data. In fact, ggplot2 provides a number of geom functions for rendering layers of different types of geometric objects. The first list gives a list of these geom functions, while the second list gives a list of geometric objects. The latter is shorter because some geom functions use the same types of objects as building blocks. For example, both geom_bar and geom_histogram use bar objects as building blocks. As we saw on the previous slides, there are many other variables in the MPG dataset. To represent additional variables in the plot, we can use other aesthetic properties of these points, like color, shape, and size. These work in the same way as the X and Y aesthetics. Suppose we are going to represent the class variable and the cylinder variable with the same set of points. Here, we add them into the call to the AES function and map them to two aesthetics, color and size, respectively. This gives each point a unique color corresponding to its class and a unique size corresponding to its number of cylinders. Since almost every plot maps a variable to X and Y, naming these two aesthetics is tedious. So the first two unnamed arguments to AES will be mapped to X and Y. As a result, all data points in this plot are colored and also vary in size. And two legends are automatically included. They allow us to read data values from the color and the size. And there are various aesthetics available to use. But each type of geometric shapes can only display certain aesthetics. This chart gives you an idea of what aesthetics are available to what geometric shapes. Some of them are required for a geo, while others are optional. If we try to create a geom without one of its required aesthetics, we will get an error. For example, when using a set of points, we must specify their x and y positions. And we can also specify their colors, shapes, sizes, etc. However, it is not sensible to specify the height, width, or angle for a point object. ggplot2 allows us to supply aesthetic mappings in different places. We can supply a mapping in the initial ggplot call, in individual layers, or in some combination of both. And all calls listed in this cell create the same plot specification. Generally, the mappings set in the initial ggplot call will be inherited by subsequent plotting layers. But we can also override these common mappings in a specific layer. For example, suppose we have mapped the displacement to x and mileage on the highway to y in the initial ggplot call. If we then map different variables onto x and y in a subsequent added layer, the new mappings will override the common mappings in determining the x and y aesthetics of geometric objects in this layer. We can also remove an existing mapping for a layer by overriding its value with null. Establishing aesthetic mappings in the initial call should be used with care, because it will affect all subsequent plotting layers. By comparing these two plots, you can find that the color mapping specified in this ggplot call also takes effect in the layer of smoothed lines, resulting in multiple colored lines, each corresponding to one value of this class variable. One remark I would like to make here is that as a type of graphical elements, lines are different from points. While we need only one observation to draw a point, we need multiple observations to determine a line, which could result either from drawing these observations or from fitting a smooth curve to these observations. So multiple lines in this plot are estimated from different groups of observations, which implies observations have been assigned into different groups in advance. And there's a special aesthetic named group that controls the assignment of observations to graphical elements like lines. By default, the group aesthetic is mapped to the interaction of all discrete variables in a plot. In this case, because class is the only discrete variable, observations are grouped by class. This grouping rule often partitions the data correctly, but when it does not, we'll need to explicitly define the grouping structure by mapping the group aesthetic to a grouping variable. In this example, we will use a simple longitudinal data set, aux points from the NLME package. It records the height of 26 points, measured on 9 occasions defined in terms of ages. So each boy had his height measured 9 times. And the observational unit in this dataset is one of these height records. Let's first create a box plot to explore how distribution of boys' heights vary across ages. This is created by mapping occasion to X and height to Y, and adding a layer of boxes. And each box is created by calculating the quartiles of the 26 height records measured on the corresponding occasion. In addition to the change in the distribution of heights, another interesting pattern we may want to investigate is the change in height at the individual level. What if we want to find all height records for a boy at his different ages and connect them to form a growth trajectory for that boy? What if we want to do so for all boys in this dataset? As we know, lines are suitable graphic elements for representing trends and changes. And there's a geom line function that we can use to add lines formed by joining observations. But if we just apply this function naively, we end up with a set of vertical lines, each of which is formed by joining all 26 height records measured on the corresponding occasion. Why is that? The reason is that the line layer inherits the plot aesthetic mappings, which by default map the group aesthetic to the discrete variable used in this plot. That is occasion. So now we need to override this default grouping by setting the group aesthetic explicitly to the variable subject, which identifies individual boys in this dataset. Eventually, we get the desired growth trajectories for all boys in this dataset. This enriched plot reveals some interesting things about the data, like the lowest height records across all 9 occasions were measured from the same boy. A remark I would like to make here is that instead of mapping the color aesthetic to a variable, I specify it outside the call to the AES function and set it to a constant blue. Setting an aesthetic without calling AES makes all geometric objects used in that layer affected. That's why all these newly added lines are colored blue. In some situations, rather than raw data, we are more interested in displaying some form of statistical transformations of data. It requires computing some summary quantities first, and then map the computed quantities to aesthetics of a geom. Then, how can we achieve this type of goals? Do we have to first go to other tools to manually transform data, and then come back to ggplot2 to plot results? The answer is no. In fact, ggplot2 provides a one-stop solution for plotting statistical summaries. In this example, we use another categorical variable, trans, standing for type of transmission, to define the x-axis. Suppose in addition to the points that represent the raw data, we want to add another set of points to denote the means of miles per gallon for city driving for different types of transmission. As you can see, the geom point function has a parameter named stat, which defaults to identity, meaning the display of raw data. In the second call to the geom_point function, I override this default value with the string summary, indicating that this new point layer is going to display some sort of a summary quantities. Then I set another parameter, function y, to min, indicating we are going to use the results of min calculation to determine the y coordinates of these new points. Lastly, I set the color and size aesthetics to constants so as to give these points a different style. As a result, we have a new set of points overlaid on top of the original set of points, denoting the average heights across these 9 occasions. In fact, the ggplot2 system conceptualizes statistical transformations as a distinct grammatical element called the stat, and provides a class of more specialized functions for displaying statistical quantities. For example, here, instead of using a geom function that focuses on the visual appearance, we use a stat function that draws more attention to the statistical transformation. And we specify the geom to use to be points, overriding the default choice point range. And you may find that function y is actually a formal parameter of this stat function. And it gives us the same layer of red points as the previous geom function did. ggplot2 also provides a number of stat functions to create a variety of statistical transformation objects. The first list gives a list of these stat functions, while the second list gives a list of statistical transformation objects. Like geoms, stats also responsible for rendering plotting layers. We can use both of them to overlay data elements in a plot. Many stat functions have geom equivalents. And as geom functions have default stats, stat functions also have default geoms. As you can see, the default stat of the geom histogram function is bin, standing for binning, because to construct the bars that make up a histogram, the first step is to bin the range of values. That is, divide the entire range of values into a series of intervals, and then count how many values fall into each interval. This is why its stat counterpart is the stat_bin function, whose default geom is bar. And we end up with the same histogram with these two interfaces. It is generally possible to create the same plot with these two classes of functions. This example demonstrates how we can reproduce our plot for the Oxbourne's dataset using the stat summary function by setting geom to line. And since observations have been grouped by subject, although we set the function y keyword to median, the median calculations are each performed on a single observation, and no aggregations actually happen. Then What if we want to draw a single curve that connects the median height across these occasions and annotates this box plot with the corresponding trend? What we need to do is to set the group aesthetic to 1, indicating that all observations on an occasion should be combined into a single group. As a result, the median function takes all height records measured on an occasion and finds their median. And the stat summary function uses these values to determine the positions of a set of hidden points used for forming this curve. What if instead of the median, we want to display the trends in the first quartile and the third quartile? Recall that the quantile function can be used to compute these two statistics. But we have to supply the arguments to its probabilities parameter. And this is done by using this function arguments keyword. But if we attempt to overlay these two statistics with a single layer, we cannot get the desired output, since all statistics are used to form this single curve. So the correct way is to render two layers of statistics, one for the first quartiles and the other for the third quartiles. Actually, a statistical transformation is able to produce more than one summary quantity. For example, binning used to make histograms can produce the number of observations in each bin and the density of observations in each bin. By default, the histogram geom assigns the height of the bars to the number of observations. But we can also assign the height of the bars to other summary quantities like the density and normalized count, as shown by these two examples. And to refer to a generated quantity, like normalized count here, double dots must surround the name. This prevents confusion in case the original dataset includes a variable with the same name as a generated quantity. And to know the list of quantities created by a statistical transformation, you need to check its documentation. Sometimes, with dense data, we need to adjust the position of elements on a plot to give them a better presentation. Position adjustments apply minor tricks to the position of elements within a layer. And they are the last layer-related grammatical component in ggplot2's conceptual model. Both stat and geom functions have a parameter named position, which we can use to specify how we want to position graphical elements created by them. In this example, I create a bar plot and map the variable fl, standing for field type, to x, and the variable class to the aesthetic of filling color. So within each level of field type, the observations are further partitioned by class, and a bar is created for each partition and colored differently. And the default way to position these bars is to stack them. But we can override the default value to position these bars differently, like dotting them. Here I also use the options provided by the theme component to suppress the creation of legend, so as to enlarge these two plots. ggplot2 also provides a set of position prefix functions to give us fine-grained controls over positionings of different types of elements. In this example, I create a box plot and map class to X and displacement or engine size to Y. And I further create a discrete variable on the fly, which indicates whether displacement is above or below a threshold value, and map it to the color aesthetic. In the resulting plot, for each class of cars, a pair of boxes are created, representing different groups resulting from splitting car observations by that discrete variable. However, some pairs have one box missing because cars of those classes have their engine sizes either all above the threshold value or below that value. And we end up with boxes with varying lengths because by default, the ggplot2 function attempts to preserve the total width of all boxes clumped at the same location. If you are not happy with this arrangement, you can use this position adjustment function to indicate the ggplot2 function to preserve the width for each single box. You can also use other parameters to further control the arrangement of these boxes. For example, use padding to adjust the padding between boxes at the same location. Now, perhaps it's a good time to summarize the grammatical elements we've discussed so far before moving forward. To create a plotting layer with ggplot2, we need to first have a data frame that contains all the data to be plotted. Then, need aesthetic mappings to describe how the data are mapped to things like colors, sizes, shapes, etc. And geoms are specific objects that we are going to put onto the graph. There are things like points, lines, polygons, bars, or whatever. And then stats are statistical transformations like smoothing, binning, quantiles, regression, things like that. And we use them to summarize data in many useful ways. Lastly, we need position adjustments that deal with overlapping geometric objects. And these 5 grammatical elements together form a layer for plotting data.